All right, so let's go ahead and talk through how to figure out what's being oxidized and what's being reduced. So the first thing that would be helpful would be to have a definition of what it means to be oxidized. So what are we looking for when something is oxidized? Which means that reduction is, yep. And we're going to be able to tell if each of these elements has gained or lost electrons by checking out what's going on with their oxidation numbers when they're a reactant and checking their oxidation numbers when they're a product. So if we start with A, we want to figure out what happened to silicon. So when I have an element just chilling by itself being a solid, what does that mean for its oxidation number? Yeah, so it started with an oxidation number of 0 here. What's its oxidation number on the product side when it's in SiCl4? What do we get for that one? Yep, so we know here that we're going to have a +4 oxidation state, and the way we know that is because chlorine is fairly easy. What's the oxidation number of chlorine most of the time? -1, okay? And since there are 4 chlorines, that means that the one silicon has to be +4. So if Si went from being 0 to being +4, what did it do? Did it gain electrons or did it lose electrons? How do you get to be positive? You lose electrons, right? Because if you lose something negative, you're now positive. So that means that Si was oxidized or reduced? Oxidized. So really, without even trying, you know for sure that chlorine must be reduced. Why? Exactly. That is the entire point of a redox or reduction-oxidation reaction, is that the electrons that are lost by one substance need to be gained by the other one. They always occur simultaneously. If something is being oxidized, something is being reduced. If you don't see both things happening, it's either because it's an incorrect reaction or you're looking at what we call a half reaction, which means we're only looking at one piece of it, either oxidation or reduction at a time. So let's just confirm that we can see that happening for chlorine. So when chlorine's just hanging out as Cl2 as a gas in its natural state, what's the oxidation number of chlorine? 0. This is how chlorine naturally occurs. It's not in a compound, so it's 0. So we can say that chlorine went from being 0 to -1. Well, how did it do that? How do you go from being 0 to being -1? What did you do to your electrons? What's the charge on an electron? Negative, so you must have gained it. So we know for sure that this is reduced. Any questions on how I was able to make that identification? Okay, so that one was pretty straightforward. B is a little weird, okay? So if you look at B, how many different elements are there in reaction B? There are 3, but I can only have one thing being oxidized, one thing being reduced. So what does that mean about the third thing? Spectator. It's essentially a spectator. Nothing is changing about it. So I'll give you about 15 seconds, talk to your neighbors, see if you can identify which one of those was not changing. All right, let's see how we did. So I'm going to do this the same way I did the other one. I'm just going to start from the left-hand side. So I'm going to start with chlorine. You already told me that when chlorine's in its natural state, it's got an oxidation number of 0. When it's in the compound NaCl, what's its oxidation number going to be? When it's in a compound? Can't be 0 anymore. It's going to be -1 because we know that sodium is going to be +1. So that means that chlorine, again, went from being 0 to -1. So we know that chlorine was what? Okay, let's do the same thing for the sodium. So when sodium is in NaBr, we can kind of play this from either side, what do you think the oxidation number of sodium is in that compound? +1. It's in an ionic compound, which means that the bromine is going to have to be what? -1, and that's reasonable because bromine's a halogen, so that's pretty normal for it. So if I look at what happened to sodium, sodium went from being +1 to being +1. Did anything change about sodium? there's your spectator. Okay, nothing changed about it. It was not oxidized or reduced, which means that we're pretty sure that bromine is going to have to do what? Yeah, we're pretty sure bromine's going to have to be oxidized, but we should really prove it to ourselves. So you already told me that when bromine was in the compound as a reactant, it had a -1 oxidation number. What about bromine as a product? Br2 aqueous, the oxidation number there. That's 0. That's the standard state of bromine. So how do you get from -1 to 0? Careful, what's the charge on an electron? Negative. So how do you go from having a negative charge to none? You've gotten rid of your electron. So we know that getting rid of your electron, oxidation. So that confirms what we think should have been happening in that reaction. All right. So the first thing you want to do with a question like this is you want to think about everything that you have in solution. So we're first going to go through each of these compounds and try to figure out what they're going to break into when they go into solution. So what is the name of this compound here? This is lead 2 acetate. So that tells me that I'm going to have lead ions and I'm going to have acetate ions. So you should notice that there are 2 acetate groups attached to this. We know that each acetate group has what charge? -1. So since it took 2 of those to balance the charge on the lead, what must be the charge on that lead ion? Which is how we knew it was lead 2 acetate. Okay, so now we know we've got lead ions and acetate ions in solution. We've got sodium sulfide, so that's going to give us sodium ions and sulfur ions, and then the calcium chloride is going to give us calcium ions and chlorine ions. So now I've got a bunch of things in solution, and this is the point at which essentially what you're doing is you're trying to figure out what possible combinations could I have and how are those soluble or insoluble. So something that I think is fairly easy to do is look for things that are either always soluble or always insoluble. That way we just know for sure what's going on with them. So do you recognize anything from there from the solubility rules that was always going to be soluble no matter what it was paired with? Acetate. So one of the solubility rules says acetate is always soluble. So that essentially tells me I don't need to worry about that forming any sort of precipitate because I know that it's just going to be floating around in solution. So I'm just going to cross it out because I don't need to worry about it right now. Okay? Is there anything else that's essentially almost always soluble? It shows up in kind of a tricky way. It showed up in an exception sort of way. Sodium, okay, so if you looked at the insoluble part, the bottom part, you'll notice that the exceptions are always the alkali metals. Alkali metals tend to make things soluble, so sodium, always going to be soluble. Okay, so we don't really need to worry about making compounds with that. Now, essentially what we can do at this point is we can think about all the other possible compounds that could be forming, and we can check the solubility rules for that. So we can see that lead could combine with the sulfur. Can lead combine with the calcium? No, those are both cations. That's not going to work. So what else could lead combine with? Okay. I've already combined the sulfur with the lead. Sulfur could also combine with the calcium. All right. And then the only other combination I have is CaCl2. But we already know that that one's soluble, right? Because that was one of our original things. So that's not going to recombine. I really don't need to worry about that. Okay, so let's talk about the lead sulfate, the lead chloride, and the calcium sulfide. Sorry, lead sulfide, lead chloride. So do you recognize any of those from the solubility rules? Any of those as being definitely soluble, definitely insoluble? Yeah, sulfides are usually insoluble. The only time it would be soluble is if it was with like an alkali metal, but we already crossed out the sodium, so we don't need to worry about that. So this one is definitely going to precipitate. Do you recognize anything else on there from the solubility rules? Okay, so again, we talked about the sulfur is one of our usually insoluble compounds, but calcium is another exception there. So this is going to be aqueous, all right? And then the lead chloride, somebody said it. So chlorides are usually soluble unless they're with silver or lead. So those are going to be my two solids. This one's pretty straightforward, is because they're giving you guys everything in moles. So this one should be pretty fast for us because we don't have to worry about any gram to mole conversions. If I did need to convert between grams and moles, what's the one piece of information you need to do that? Periodic table, so you can calculate molar mass. Good. Okay, so for those of you guys who have looked at the videos I put up for your class, I do my limiting reactant problems in a very specific way, and I do it by creating something that I call an ICE table, which stands for initial, change, and end. So essentially what I put in the ICE table is I always put moles in, so if I get something in grams, I'll convert it to moles. And with this ICE table, I try to figure out what's going on with my ratios of reactants and making products. So all I'm going to start by doing is writing in the information that I know. So I know that I have 1.85 moles of NaOH, and I know that I have 1.00 moles of the carbon dioxide. And again, this ICE table only works when we're talking about moles, so I would have converted anything in grams into moles. How much of the products did I start with? What do we think? Did they tell us anything about it? No. So we can assume no products there. The change row is really the most important one. This change row is also based on the coefficients. You can think of the C as standing for the coefficients. So if I look at this reaction here, can you see that I consume 2 NaOH for every 1 CO2? You see where I'm getting that ratio from, the 2 to 1? So what happens to the reactants as we go through a reaction? Do we make more of them or do we consume them? What do you do to reactants during a reaction? You consume them. That's the whole point of them. So because of that, I'm going to give this a negative sign. So the -1 and the -2 are coming from those coefficients because that's how much they're changing by. The first one is changing by a factor of 2. The carbon dioxide is changing by a factor of 1. I'm going to put an X in there because I don't know how many times I'm going to be able to run this reaction. If I think about it for the product side, if the reactants decrease, the products better be increasing. Coefficients here, 1 and 1, so I can think of this as plus 1x and plus 1x. I realize that I'm blowing through this if this doesn't make any sense and you're just like, whoa, that's fine. But for those of you who have been watching the videos, this might make more sense. So essentially what I'm doing now is I'm saying, okay, I know that I consume my NaOH in a 2 to 1 ratio with my carbon dioxide, right? So if I look at the amount I started with, did I start with a 2 to 1 ratio? Do I have enough of the NaOH? No. I don't have enough NaOH. There's no possible way that I can consume all of the CO2 because in order to consume all of the CO2, how many moles of NaOH would I need? 2, but I don't have those. So depending on how you want to do this, I like to set up a little just algebraic thing for me. So I know that at the end, I'm going to have none of this NaOH left over. I didn't have enough of it. It's my limiting reactant. So I know that essentially 1.85 moles minus 2x equals 0. I can solve that out and figure out that x equals 0.925 moles. So I can plug in my x for this table here, and now I know that I started with 1 mole of CO2. I consumed 1 times 0.925. So what's 1 minus 0.925? Yep. And here I know that I increased by 1x, so this is just going to be 0.925 and 0.925. So now I can essentially go through and answer these questions. What is the limiting reactant? Well, we figured out that the limiting reactant was the NaOH. How many moles of Na2CO3 can be produced? 0.925. How many moles of the excess reactant remain? 0.075. So that's why I do it in the ICE table, because I do kind of a lot of work up front, but then I can directly get all of the answers that I need. Again, if that was a little confusing, I apologize. That's just my standard way of doing these kinds of problems. You can use normal stoichiometry, and you should have gotten exactly the same answers. This is just another way to do that.